Check it out now, y'all.
nanoHUB-U, online instruction.
Well, in the last lecture, we talked in a little bit of detail about the physics of carrier scattering. I want to continue that discussion in this lecture and talk in some detail about transmission, and the physics of transmission. Just like week 3, the first 2 lectures of this week are a little bit mathematical. We're going to discuss some concepts and derive some formulas, and then in the next lecture we'll begin to apply that and use it, and we'll get more and more comfortable with it. Okay, so let's talk about transmission. We're going to analyze a simple model problem here. I'm going to think about a region that has a mean free path that's constant. It's a region of length L, so obviously we're thinking about the channel length L of a MOSFET. It has no electric field, so we'd be thinking about a MOSFET under very low drain bias where the electric field is very weak. And I'm going to assume that the mean free path is constant all across the length of that region. And the physical picture is that we inject a stream of electrons, that's called I sub 1, in some energy channel E at x equals 0 from the left. Some fraction t transmits across, elastic scattering, so it comes out at the same energy, and some fraction r reflects back. So what doesn't come out the right goes back out the left. Nothing recombines inside the slab. So that's the physical picture. And what we would like to do is to compute this t and to see that this expression, mean free path over mean free path plus length, that I've just been writing down as something that's plausible, we actually want to derive that and see where it comes from. Now, we could do the problem in the reverse way. We could inject the stream of electrons from the drain. Some fraction t will come out the left contact. The rest of them, what don't come out the left contact, will backscatter and return to contact 2. As we discussed in the last lecture, we're only going to be considering one transmission. If this is elastic scattering, the t's in both directions are the same. And I have an absorbing contact here. In both cases, I had an absorbing contact, which means nothing comes in from the absorbing contact. Things only go out. Okay. So in general, we could have injection from both. And as we discussed in the last lecture, for elastic scattering, there's only one t. Near equilibrium, things should be symmetrical. So even if there is a little bit of inelastic scattering, we can think of just one t. And under high bias, that's a problem that we will discuss later. But only one of the t's will be large enough to worry about. Okay. Okay, so we're only going to do one of these problems because t is the same in both directions. So let's do this one. Just like before, I'll eject from the left. I'll try to calculate t. The problem is specified that we have an absorbing contact at x equals L, which means no electrons come in from the right contact. We're going to ignore any kind of inelastic scattering here. So t sub left right is equal to t sub right left. And our goal is to relate t to the properties of this slab, basically to the mean free path. We're not going to make any assumption about whether the slab is many mean free paths long or whether it's short compared to a mean free path. It can be ballistic, it can be diffusive, it can be anything in between. Okay, so let's get started, and there'll be some algebra. We'll just go through this step by step and you'll see how it works. So we inject a positive flux. Once the electrons get inside, there will be some backscattering. Some of that positive flux will backscatter and become a negative flux. Then some of that negative flux that begins to build up will backscatter and become a positive flux. So inside the slab, I'm going to have both a plus and a negatively directed flux, and they're going to be spatially varying from one side to the other. This is what we're going to want to calculate. What we're going to be interested in is the positive flux that comes out at x equals L. That's what emerges, and that is what, by definition, is transmission times what came in. And we want to compute that t. And then r is just 1 minus t, so we can get that easily. All right, so we can write down a little equation for what goes on inside the slab. If I ask how the positive flux varies with position inside the slab, you can see that backscattering is going to reduce the positive flux because it'll make it a negative flux. So I'll have minus the positive flux divided by the mean free path. I'll interpret this as the probability per unit length that a positive flux is converted to a negative flux. This is actually my definition of mean free path for backscattering in this particular context. So this is basically a defining equation for our mean free path. Now, once I have some negative flux, though, that'll build up, if the negative flux backscatters, it becomes a positive flux. So there's a plus sign there that will have the positive flux grow. That's the differential equation that I have to solve inside the slab to find how the positive flux varies with position. Now, one important thing is that if I look at the net flux, I plus minus I minus, that has to be constant because, this is Kirchhoff's current law. The total current has to be constant unless there's some generation or recombination source inside the slab, and we've ruled those out. So the net current is spatially constant. That means that I could solve for the negative current, it's just the positive minus the net current, and I could plug it into my equation, and I would get a simpler differential equation for the positive flux. The derivative of the positive flux with respect to position is just minus the net current divided by the mean free path. And the net current is a constant. So this is a very simple differential equation. It's one that we can easily solve. Okay, so let's begin with that differential equation and let's solve it. So let's integrate from 0 to the end of the slab. I'll separate the variables, so I'll integrate from I plus at x equals 0, and I'll find I plus at some position x in the slab, and I'll integrate dx prime from x equals 0 to some location within the slab. Current and mean free path are assumed to be spatially constant, so I can pull them outside the integral. And that's an easy integral to do. And it says that the flux is what it begins with at x equals 0, and then it just decays linearly with position. You might have guessed that it would decay exponentially, but the fact that the negative flux that builds up backscatters and then adds to the positive flux makes it turn out that in the end, when you include both of those contributions, you just get a linear decay of the positive flux with position, not an exponential one. Okay, so first part of our problem is solved. We have an equation for the position-dependent positive flux within the slab. Now, that position-dependent positive flux, let me revert back. The net flux is the positive flux minus the negative flux. So I'm just reverting back to expressing everything in terms of both positive and negative fluxes. So I now have an expression for the positive directed flux within the slab. I'm interested in what comes out. So I'm interested in the positively directed flux that emerges at x equals L. So I'll put x equals L. This is my incident flux. I'll put x equals L. I'll put x equals L for the negative flux too. Okay. Now, the problem was stated that I have a contact here that's perfectly absorbing. And we'll see that that's generally a very good approximation for the problems that we're going to be looking at. That means there is no negative flux coming in at x equals L. So I can set that term to 0. And when I do that, I have an equation that just relates the positive flux that emerges to the positive flux that entered. And that's an equation that I can solve for the ratio of the two. So this is the equation that we have developed so far. All I have to do now is to solve that equation for what emerges from the left. And I'll get what came in divided by 1 plus length divided by mean free path. By definition, the ratio of what comes out to what went in, that's what we call the transmission. And if I simply take that ratio, the transmission is mean free path over mean free path plus length. So you can see we've derived this expression that we've been using. We haven't made any assumption about whether the slab is many mean free paths long or whether it's only a fraction of a mean free path long. It applies from the ballistic to diffusive limit. When the slab gets very long compared to a mean free path, the transmission gets very small and we're in the diffusive limit. When the slab is very short compared to a mean free path, the transmission approaches 1 and we're in the ballistic limit. Conservation of electrons just says that T plus R is equal to 1. So we've derived this expression that we saw at the beginning of the course, and we see that it comes from a simple solution of a very simple Boltzmann equation, for those of you that have seen the Boltzmann equation before. Okay, so we've derived an expression for the mean free path, but you'll notice that I gave it a different symbol than the product of velocity times tau. Now this is something that we have to be a little bit careful about, because many times when you read papers you have to ask, what mean free path is the author talking about? The most common mean free path is this one, just the distance between scattering events. But we're asking for something a little bit different. We're asking for this mean free path for backscattering. You know, this is the length of the slab. Such if the mean free path is the length of the slab, then the transmission is 1/2. If I'm using the mean free path for backscattering, and that's what comes out naturally from this Landauer approach. So I have to talk about the connection between these two. And we can do it this way. You know, it's easiest to see this in 1D. What if I had an electron coming in on a nanowire and it encounters some scattering potential? Two things can happen. It could forward scatter. Let's say if the scattering is isotropic, so in 1D I only have two directions, forward and reverse. If the scattering is isotropic, what that means is I have equal probability of scattering forward and back. I could scatter forward or I could scatter back. If I scatter forward, nothing has really happened. The electron continues along in its normal direction, and it's as though nothing has happened. So the average time then between events that cause a backscattering is not the scattering time, but it's twice the scattering time. That means that if I want the mean free path for backscattering, it is twice the mean free path. Okay? So the mean free path for backscattering is always going to be longer than the mean free path for scattering itself. Now it's a little harder to see in 2D. I'll just state the result, but I'll tell you why it occurs. And some of the chapter references discuss this in more detail. So let's think in 2D. So I'm looking down on the XY plane. Electrons come in. They might backscatter at some angle x. They might backscatter at a higher angle. Both of those are, well, the first one is actually a forward scattering event. We've lost some forward flux, but not very much. The second one is a backscattering event, which we've lost more forward directed flux. You know, this one is an even more severe backscattering event. So I have to properly average over these angles in order to get the appropriate average mean free path to convert a positive stream of electrons into a negative stream of electrons. As I said, I'm not going to go through that calculation. It gets a little bit tedious. There's some references to go through it for you if you're interested. But the final result is that in 2D, the mean free path for backscattering is pi/2 times the actual mean free path. So you'll sometimes be reading papers and people will quote a mean free path and it might be about 1.5 times shorter than you think it should be. That's because you're using the mean free path for backscattering, you're working in a Landauer formalism, and they're using a different mean free path. So be aware of that and look out for it. Okay. So we have discussed this easy problem when the electric field is 0. And we've got a very simple answer, and we've defined our mean free path in such a way such that when the length of the slab is 1 mean free path long, the transmission is 50%. That's the way we've defined the mean free path for backscattering. But now we need to ask, what happens if there is an electric field in this slab? If there's an electric field in that slab, then we need to calculate, this is like a MOSFET channel under high electric field. Now, Here we get into much more complicated problems in transport physics, where people do things like Monte Carlo simulations. So we're going to try to get the gist of what happens here and try to do it in a way that we get the key physical insight without doing the detailed calculations. So how do we understand that essential physics? Well, we do those detailed calculations, and then we try to understand what comes out of them. Now, these are some calculations that were done by Peter Price at IBM quite some time ago. He was looking into what happens when you inject a stream of electrons into a slab with a very high electric field. And he was tracking them through by Monte Carlo techniques on a computer. And he noticed something very interesting. If an electron got just a little ways into this electric field region, or down the potential drop, then even if it scattered, it really didn't matter. The electron was bound to come out the right side. So there was just a very small critical layer at the beginning. If electrons scattered there, they could backscatter and return to the first contact. If they got across that critical region, I'll call it a critical layer with length script L, then even if they did scatter, they were bound to come out the other contact. So that's a very interesting result. You know, it came out of a lot of detailed calculations. And what it means is that the transmission can be quite high even though there's a lot of scattering, because the electron doesn't need to go ballistically across this high field region. It just needs to go out contact 2. And these scattering events here, very difficult for the electron to turn around and get over that potential energy barrier. So the moral is that high electric field regions are very good collectors of particles. They're very good absorbing boundary conditions. Most of the electrons that come into that high field region are just swept out the other contact and are not backscattered into the contact that they came from. Now we can look at this a little physically and see if we can understand it. Let's say an electron comes in and undergoes a scattering event. It has a significant amount of additional kinetic energy that's been gained by that potential drop. And the question we're asking now is, what's the probability that it can turn around and return to the source and not transmit? Well, if it's an inelastic scattering event and it loses energy and drops down, then it's very hard for it to absorb energy and get over the barrier and out again. But even if it's an elastic scattering event, it turns out to be hard for it to get back to the contact it came in at. And we can kind of see that this way. The electron comes in at some direction to the XY plane with some initial momentum. It gets accelerated by this electric field or potential drop, so it gets a bigger momentum in the direction of transport in the X direction. Then it backscatters. If it backscatters isotropically, it can go in any direction. But it can't get back out over this barrier unless it has enough momentum directed along the X direction. It has to have 1/2 mvx squared greater than this potential drop in order for it to get over the barrier. So if it's injected at an angle, it won't have enough momentum in that direction to get over the barrier and out. So it turns out that even in this elastic situation, where the electrons are not changing energy, there's just a very small cone of electrons that are backscattered almost directly back at the source that are able to get out. So most electrons, even if they scatter, are not able to get out. That's the essential physics of what's going on. Okay, now I want to make it a little more realistic. For those of you that are familiar with bipolar transistors, will remember that we can think of the base as a neutral region with no built-in field, and we can think of the collector as a high field region. But this is also the way a MOSFET is designed when it's electrostatically well tempered. There is a low field region near the source, and then most of the electric field and potential drop occurs near the drain. So this composition of a low field region followed by a high field region is what we would see in a MOSFET under high drain bias. So let's say we have 2 different lengths here, and we want to know what's the probability that we will transmit across the entire structure, which would be our channel under high drain bias. Well, we've just seen that the high electric field region acts as a very good collector. Almost everything that's incident there is collected. The region with no electric field has a very simple expression for transmission, mean free path over mean free path plus length. So what it means is that the transmission across this composite structure is very nearly equal to the transmission across the part of it that has a low electric field. All right. So that's an important point that we're going to make use of when we talk about transistors, that transmission is controlled by the low field region. Okay, so we've covered a lot of ground, so let me make some key points here. Transmission is related to the mean free path, remember, for backscattering. So it's a specially defined mean free path given by this particularly simple formula. We know how it simplifies in the ballistic limit. We know how it simplifies in the diffusive limit. We've seen that regions with high electric fields are very good collectors. They have a transmission of about 1. And that when we have a structure that has a low electric field followed by a high electric field, it's the low field part of it that really controls the transmission. Okay, those are the main points, but in the next few minutes I want to do one more thing and make one more point and derive one more result that we've seen a few times. So if you'll bear with me, we have a little more algebra to do, but I'll try to show you how all of this works out. I want to relate the mean free path to the diffusion coefficient, because this turns out to be something very useful for us. So let's look a little bit more closely here. At x equals 0, we have two kinds of electrons, some moving in the positive direction at a velocity, some moving in the negative direction at a velocity. Let's assume the velocities are isotropic, so the velocity in the positive x direction is equal to the velocity in the negative x direction. If I want the total number of electrons at x equals 0, I'll just add the ones with positive velocity and the ones with negative velocity. The ones with negative velocity are just r times the ones with positive velocity. So I get that simple expression for the number of electrons at x equals 0. Well, t plus r is equal to 1 since particles are conserved, so I could write that in terms of the transmission as well. Okay, so I have an expression for the total electron density at x equals 0. I could do exactly the same thing at x equals L. I have positive velocity electrons. It's simpler now because I have no negative velocity electrons because I'm assuming an absorbing boundary, maybe a very high electric field region there. So again, I will add the two together, but the total density for electrons at x equals L is just the positive contribution. And the positive contribution is related to I plus at x equals L, which is just transmission times I plus of x equals 0. All right, so what can we do with that? We have the electron density at x equals 0. We have the electron density at x equals L. It's not too difficult to show, and I'll let you think about that a little bit, that within the device, the two vary uniformly. So we have n of 0, we have n of L, and the variation is uniform inside. We developed a simple expression for n of 0 and a simple expression for n of L. So this is what it looks like inside the device. So we know how the electron density varies inside the device. If I subtract the two, I can develop an expression for the difference. If I solve this expression for I plus of x equals 0, and then multiply by the transmission, that's the net current that comes out. That's the net current that is flowing in this structure. So solve for I plus, multiply by t, and this is what I get. Okay. Now that still looks a little bit strange, unfamiliar maybe, but let's look at it. What I have here is just minus the gradient of the electron density. What I have here are some constants. Let me call them a diffusion constant. So what I have here is that current is diffusion constant times minus the gradient of the electron density. Okay. So that's something that's familiar. That's actually something that we call Fick's law. Current is minus diffusion coefficient times the gradient of the carrier density. Carriers flow down a concentration gradient. We have an expression for the diffusion coefficient. Okay, so we see that under this case, Fick's law works. We have an expression for the diffusion coefficient. We know what the transmission is. We can just plug things in, and we can get a simpler expression for the diffusion coefficient. This is a very useful expression that I've used once or twice in the course and that we'll use again. There's a very simple relation between the diffusion coefficient and the mean free path. So the diffusion coefficient is the average velocity in the direction of current times the mean free path for backscattering divided by 2. That's frequently a very simple way for us to estimate what the mean free path in a semiconductor is. And there's something very curious that has happened here. You know, those of you that are familiar with Fick's law know that it's usually stated that Fick's law assumes that the region that you're dealing with is many mean free paths long. It makes a diffusive assumption. But notice, when we did this calculation in terms of these incident and emerging fluxes, we made no assumption about whether the region was long or short compared to a mean free path. And yet, in the end, we found that Fick's law was satisfied. What that means is actually that Fick's law works even in regions that are short compared to a mean free path, if we're careful about the boundary conditions. That's something that's not widely appreciated, but actually William Shockley discovered in 1962, I believe, and I'll list that as one of the references on this lecture. But it's kind of an interesting byproduct that comes out of this flux analysis. Okay, so here are the key points again. We went through those just before I talked about diffusion coefficient. So those are the takeaway points from this lecture. And then we were also able to derive the relation between the diffusion coefficient and the mean free path, which gives us a way experimentally to deduce what the mean free path for backscattering is in a particular semiconductor material. Okay, lectures 1 and 2 have sort of set the stage and explained a number of concepts, done a lot of mathematics. We're now ready to dive into how this all plays out in a MOSFET, and we'll do that in lecture 3. Thank you.